Kepler had no use for the endless revelry. He was impatient to see Tycho's data, but Tycho would give him only a few scraps at a time. Tycho, he said, gave me no opportunity to share in his studies. He would only, in the course of a meal and in between other matters, mention, as if in passing, today the figure of the apogee of one planet, tomorrow the nodes of another. Kepler was ill-suited for such games, and the general climate of intrigue offended his sense of propriety. Their cruel mockery of the pious and scholarly Kepler depressed and saddened him. My opinion of Tycho is this. He's superlatively rich, but knows not how to make proper use of it. Tycho possesses the best observations. He also has collaborators. He lacks only the architect who would put all this to use. Tycho was unable to turn his observations into a coherent theory of the solar system. He knew he needed the brilliant Kepler's help. But simply to hand over his life's work to a potential rival, that was unthinkable. Tycho was the greatest observational genius of the age, and Kepler the greatest theoretician. Either man alone could not achieve the synthesis which both felt was now possible. The birth of modern science, which is the fusion of observation and theory, teetered on the precipice of their mutual distrust. The two repeatedly quarreled and were reconciled, until, a few months later, Tycho died of his habitual overindulgence in food and wine. Kepler wrote to a friend, on the last night of Tycho's gentle delirium, he repeated over and over again these words, like someone composing a poem. Let me not seem to have lived in vain. Let me not seem to have lived in vain. And he did not. Eventually, after Tycho's death, Kepler contrived to extract the observations from Tycho's reluctant family, observations of the apparent motion of Mars through the constellations obtained over a period of many years. The data from the last few decades before the invention of the telescope were by far the most precise ever obtained up to that time. Kepler worked with a kind of passionate intensity to understand Tycho's observations. What real motions of the Earth and Mars about the Sun could explain to the precision of measurement the apparent motion as seen from the Earth of Mars in the sky. And why Mars? Because Tycho had told Kepler that the apparent motion of Mars was the most difficult to reconcile with a circular orbit. After years of calculation, he believed that he had found the correct values for a Martian circular orbit which matched 10 of Tycho Brahe's observations within 2 minutes of arc. Now, there are 60 minutes of arc in an angular degree, and of course, 90 degrees from horizon to zenith. So a few minutes of arc is a very small quantity to measure, especially without a telescope. But Kepler's ecstasy of discovery soon crumbled into gloom because two further observations by Tycho were inconsistent with his orbit by as much as 8 minutes of arc. Kepler wrote, "If I had believed that we could ignore these 8 minutes, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore them, those 8 minutes pointed the road to a complete reformation of astronomy." The difference between a circular orbit and the true orbit of Mars could be distinguished only by precise measurement and by a courageous acceptance of the facts. Kepler was profoundly annoyed at having to abandon a circular orbit. It shook his faith in God as the maker of a perfect celestial geometry. Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer. And months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law. Kepler's second law is this: a planet sweeps out equal areas in equal times. Kepler's first two laws of planetary motion may seem a little remote and abstract. All right, planets move in ellipses and they sweep out equal areas in equal times. So what? It's not as easy to grasp as circular motion. We might have a tendency to dismiss it, to say it's a mere mathematical tinkering, something removed from everyday life. But these are the laws our planet itself obeys as we, glued by gravity to the surface of the Earth, hurtle through space. We move in accord with laws of nature, which Kepler first discovered. When we send spacecraft to the planets, when we observe double stars, when we examine the motion of distant galaxies, we find that all over the universe, Kepler's laws are obeyed. Many years later, Kepler came upon his third and last law of planetary motion, a law which relates the motion of the various planets to each other, which lays out correctly the clockwork of the solar system. He discovered a simple mathematical relationship between the size of a planet's orbit and the average speed at which it travels around the sun. This confirmed his long-held belief that there must be a force in the sun that drives the planets, a force stronger for the inner fast-moving planets and weaker for the outer slow-moving planets. Isaac Newton later identified that force as gravity, answering at last the fundamental question: what makes the planets go?